like to talk a little bit about solutions, what solutions are, how they're formed, and so forth. So this will take a couple of days. We'll break this up so it's not too bad for you. Just some initial definitions. There are two general kinds of mixtures you can look at and form, heterogeneous and homogeneous. Heterogeneous mixtures are where you can see the different parts to it. Hetero, different. Genius, you're talking form, so you can see the different parts to it. A chocolate chip cookie is a heterogeneous mixture. Sand and water is a heterogeneous mixture. At the bottom of the slide here, you see mud, kind of muddy water, which is also heterogeneous because you'll notice over time it settles out. And so this clearly you can see here it looks homogeneous, but if you let it sit, it settles out and it's a heterogeneous mixture. Now, homogeneous mixtures, you have very, very small particles or much smaller particles that can stay evenly distributed. Things like salt and water, Kool-Aid, soda, anything like that, where the particles that are in there stay completely like uniform and mixed throughout, create a homogeneous. So a homogeneous mixture is also called a solution. So a solution is just defined then as a homogeneous mixture. What you have down here is really called a suspension because it's temporarily homogeneous, but over time, of course, it separates upon settling. So solutions are stable homogeneous mixtures. An example you can see here, if I'm dissolving, say, salt and water. Here are the sodium ions and chloride ions you'll see dissolved uniformly throughout the water. They're very small and they kind of stay evenly distributed. They don't settle out over time. The solute is the thing that is dissolved. So in this case, in the case of salt water, of course, salt would be my solute. The solvent is the thing that does the dissolving. In this case, it would be my water. Water is the solvent. You can have solid solutions, you can have liquid solutions, you can have gaseous solutions. Water solutions, a specific term for them is aqueous. An aqueous solution is a solution where water is your solvent. And then here's just several examples. If I dissolve one gas in another gas, I can get a gaseous solution, oxygen and nitrogen. We've talked about that before. Air is a great example of that. A gas in a liquid, something like a soda where you have carbon dioxide dissolved in the water, seltzer water. That's a gas dissolved into a liquid. A liquid into a gas would be like water vapor, humidity, that sort of thing that's going on in the air. Any liquid in another liquid, alcohol and water, two liquids that dissolve equally in one another. There's another term for that called they're miscible, M-I-S-C-I-B-L-E. They're miscible liquids. A liquid you can dissolve in a solid, mercury in silver and tin. That's what they've used for fillings in the past. These days they use different kinds of compounds, but historically you'd use this called an amalgam in there for filling. You could dissolve a solid in a liquid, sugar and water, salt and water. That's probably what you're most common with. And solid dissolved in another solid, that would be any kind of an alloy, brass, bronze. Up here on the top of the screen, you see an example of white gold where I have silver mixed in uniformly to toughen up the gold. Actually, this makes the ring a lot more durable. It helps it not get so deformed so easily because pure gold itself is a very soft kind of a metal. And again, here's some more alloys. Here's brass. This is copper and zinc. We make this when we take pennies and coat them with zinc and heat them up. The zinc and the copper blend together and you get brass. And some of you have done that with me where you get that kind of a brass look to things. So alloys are an example of a solid solution. If you have medium-sized particles, these are particles that are large enough that you can see them, but they don't settle out. And I'll show you how you can see them in a moment. One of the easiest ways is like with light. Like when you drive on a foggy day, you have colloid-sized particles of, it's like a cloud. You have colloid-sized particles of water in the air. They're not so large that they settle out of the air, but you can see the beam of headlight shining through the cloud or the fog. It lights up those particles. So you have these kind of medium-sized particles. They're not so small like on a humid day where you can't really see the water vapor. And if it's heterogeneous, that'd be rain. The particles are big enough there that they're falling out of the air. But in that case, like a fog or a cloud, they're kind of that medium-sized colloid sort of particle. A common example of that is milk, which you see here in this glass. Milk itself, right out of the cow, the cream separates. It will float up. It's a temporary heterogeneous or homogeneous mixture that does separate. So it's technically not, the cream, and you've heard the term cream rising to the top. It's not a homogeneous mixture. Now, what they will do is they will take the fat globules in the milk, that cream, and they'll bust that up into smaller particles so it stays more evenly distributed in the milk, and they make the milk homogeneous. That process is called homogenization. Milk straight from a cow has not been homogenized, and it will separate. The cream, the fat basically, will rise to the top, will come out of the milk. When they process it for you to get it and buy it at the store, it's been homogenized, a term you've seen probably on the container, where they make those fat molecules small enough that they stay evenly distributed, and that process is called homogenization, of course. So colloids usually have an electric charge, which helps them stay distributed. If you ever add acid to milk, when I was a kid, sometimes I'd dump like orange juice in there or whatever, which is very acidic, and the charge is neutralized, and you get this coagulation, you get these curds that form. Now again, here's another example. This is a regular solution. This is a colloid, a medium-sized particle thing, and you notice we're shining a beam. You can see the beam through here. The particles are staying evenly distributed, but the particles are large enough that a beam of light illuminates them and you can see them. Whereas over here, you can't really see the beam as clearly. So here's some examples of various types of colloids. And again, you don't really need to know all these, but I just wanted to give you some just examples of this stuff. Solid dispersed in a liquid, things like paints, mud, solid network extending through a liquid, it would be jello, gelatin kind of a thing. A liquid in a liquid would be the milk we just talked about, where you're taking that fat and dispersing it more evenly in the milk. Gas dispersed in a liquid would be something like shaving cream or whipped cream. Solid and gas, you can do smoke particles, things. They're big enough you can kind of see them, but they stay evenly distributed. Fog, of course, liquid and gas, we talked about that. Fog, clouds, things of that nature. And a liquid dispersed in a solid, cheese, butter, things like that. So those are just some examples of those medium-sized particles, and there are different forms that those can come in. Again, just to give you a feel for this, homogeneous things have pretty small particles, 0.01 to 1 nanometer in size. Remember, a nano is a billionth of a meter across, so these are very small. They don't separate. They go right through filter paper, and they don't scatter light, so we can't see them with a beam. The largest of the particles are the heterogeneous particles. They're over 1,000 nanometers, so these are bigger things. They can be very, very large particles. They will settle out, you can filter them out, and they will definitely scatter light if they stay suspended. Usually they fall right out and can fall rather quickly unless they're clear on their own account. Medium-sized particles are between those two. They don't separate, so they stay evenly distributed. They will go through filter paper, but the main thing is they scatter the light. So you can kind of see them, they can be illuminated, and you can see those. When ions dissolve in water, ions are charged particles, either positive or negative. They will allow the water to conduct electricity. Pure water does not conduct electricity. So why do they have you get out of a pool in the summer if there's lightning storms in the area? And that's because there's dissolved things in the water. It's not pure water. You have chlorine in there to kill germs. People may have sweated in there, so you have some salt in the water. You know, all these sorts of things that dissolve in the pool water are ions that allow that water to conduct electricity. So these are, a special term for these things are electrolytes. Electrolytes are anything that when they dissolve in water produce ions and therefore allow the water to conduct electricity. Strong electrolytes completely separate into their ions. Weak ones only produce some ions. They don't completely break apart, but they do produce a few ions. Those things that dissolve but do not produce ions are simply obviously called non-electrolytes. And let me just give you a visual on what this might look like. Sugar is a non-electrolyte. It does dissolve, but it doesn't produce ions. It's a neutral molecule. So while it dissolves, it is a solution, it is homogeneous, it does not conduct electricity. And you'll see I have a light bulb here with 2 electrodes in the water. In sugar water, does not conduct, the bulb does not light up. When you come over here to hydrochloric acid, which is a very strong acid, produces a lot of ions, H3O ions and Cl- ions. Those ions allow this water to conduct electricity between these 2 electrodes, and you'll see that lights up very brightly. Salt is also a very strong electrolyte, produces a lot of ions, and you'll see you get a very, very bright lighting of the bulb here. A weak electrolyte would be something like acetic acid. This is vinegar. Some of it stays together. So you'll see you have the complete acetic acid here. Some of them do separate into the acetate ion and the hydronium ion. But again, they don't all do this. So you get some ions, but since it doesn't completely break apart, I get some current flow. So you'll see it's a weak electrolyte, and so my light bulb here is kind of weakly lit.